All right, next lesson here, we're looking at analyzing characteristics of graphs and the relationships they have. Warm-up to get started. It says consider the sequence 4, 6, 8, and 10. Use the table to list each term of the sequence. So our inputs, our x in this case, is our term numbers. So we have term number 1, 2, 3, 4, and then our output is the term itself, which is 4, 6, 8, and 10. So using that chart, write each of the terms as an ordered pair. So we could just say 1, 4, 2, 6, 3, 8, and then 4, 10. And then last graphing those, 1, 4 would be here. And then we got 2, 6, 3, 8, and 4, 10, and we can see we have a line, so there's a linear relationship there between all those points. All right, so we're going to be looking at key terms being discrete and continuous, collinear, what nonlinear means, all in the next few pages. All right, so at the end of this lesson, there is 12 graphs we'll be cutting out. If you want to go look at them now, and ask you to sort the graphs any different ways you want. Use whatever reasoning you think certain graphs might go together, why you think they don't go together, any reasoning that you can cause a relationship between the groupings you put together. So take a few minutes, I'd pause it, try that, and then we'll come back together. All right, so a discrete graph is a graph of isolated points. So think of just a bunch of points all over the graph. They're not connected by a line. The values between each point on a discrete graph are not part of the relationship. So we might have a situation where you're talking about number of players on a team. Well, we could have only whole numbers in that situation, positive integers. So 1, 2, 3, 4. It doesn't make sense to say 1.5 players. So that's why the line is not connected between the points in that situation. So if you go look at those graphs, let's scroll to the very end to the graphs. The graphs that are discrete, that you can go back in and fill in on the lesson, are A. A would be discrete, F would be discrete, and I think there's another page of them. Yep, there's another page. And J would be discrete. So all those are just isolated points. All the other graphs, those would be continuous. Continuous is a graph with no breaks in it. So you will see a line connecting on the point. So on this page, G, H, I, K, L, those would all be continuous. And on that previous page before, E, D, C, B, and A, or C and B would all be continuous. So scrolling back up to that page, if I want to fill those in, the discrete ones were A, F, and J, and our continuous ones were all the other ones, B, C, D, I wrote another B, D, E, G, H, I, K, and L. Okay, now it wants us to sort graphs into groups by increasing, decreasing, both increasing or decreasing, or neither. So again, if I went back to those graphs, A, for instance, would be increasing. When we say increasing, we're going up from left to right. B would be increasing. Okay, C, we could say increasing and decreasing because it's going down and then back up. Same thing with D, that circle, at different points it's increasing, at different points it's decreasing. E would be decreasing only. F, neither increasing or decreasing. We got a straight vertical line. And then if we go to our other pages here, G is neither increasing or decreasing, got a horizontal line. H would be both, increasing and decreasing. I would be both. You could say at different points on I we're increasing and decreasing. J then would be neither. There's no trend at all there with J with that data. K would be decreasing, and then L would be another one where we are both increasing or decreasing. So if I go back to fill in those, the increasing ones we said were A and B. Decreasing were E and K. The ones that were doing both were C, D, keep writing a B when I say D, C, D, H, I, and L. And then the ones that were neither were F, G, and J. All right, so a linear graph is a graph that is a line. First four letters of linear are line. So it's a series of collinear points, and a nonlinear graph is a graph that is not in a line, therefore a series of not a series of collinear points. So if we want to sort those graphs now based off linear or nonlinear, if I go back to the graphs again, A would be linear, those are in a line. B is linear. F would be linear, it'd be a vertical line. G would be linear, we've got a horizontal line. And then the only other linear there would be K. So all the other ones, the points do not form a straight line, so those would be considered nonlinear graphs. So going back to fill those again, our linear ones were A, B, F, G, and K, and our nonlinear ones were C, D, E, H, I, J, and L. All right, so next we're going to look at graphs and how we can interpret meaning for the graph. So this graph shows Greg's distance from home after driving for X number of hours. So if we look at the top of the next page, analyzing the graph between 0 and 2 hours. So how far from home was Greg after driving 2 hours? So 2 hours, he's right here. So it looks like he's at 120 miles from home. So we can determine in those 2 hours he's gone 120 miles. So if we want to know how fast he was driving, he went 120 miles in 2 hours. If we divide that, he was going 60 miles per hour for that 2 hour stretch. Okay, how do we know that Greg traveled the same rate for those hours? It's because we have a straight line, which shows we had a constant rate. Okay, now it wants to know how far did Greg travel from home between 2 and 2.5 hours. So here's 2.5. So the distance didn't change. So in that time period, he went 0 miles. So if he went 0 miles, how fast was he traveling? He was traveling 0 miles per hour. He wasn't going anywhere. So the shape of that part of the graph where it was 0 miles changing created a horizontal line. So that horizontal line showed that the time was passing, but the distance wasn't changing to create a change, a rate of change there. It's just 0. All right, so labeling each segment of the graph, we can flip back and forth from the graph to take a look at this. They already filled in the first two we just named. The next one would be, and I'll go back to the graph to show it, 2.5 hours to 4.5 hours. And if I go back to the graph to show 2.5 hours to 4.5 hours, two and a half hours is here to 4.5 hours is right there. So he went from 120 miles to 180 miles. So he went 60 miles during that time period. So from 2.5 to 4.5, he went 60 miles at a rate, 60 miles over 2 hours, so 60 divided by 2, of 30 miles per hour. Okay, our next time period, when I go back to the graph, is going to be from 4.5 to 5.5. So again, scrolling back to the graph, 4.5 here to 5.5, we got another horizontal line. So he traveled nowhere. He went 0 miles. So 0 miles in 1 hour. So he took a break, for instance, from his driving. And then the next part of the segment of the graph is 5.5 hours to 8 hours. So again, going back to our graph, change colors here. 5.5 is here to 8. So now it looks like he's coming closer to home. So he went from 180 down to 130. So he traveled 50 miles during that time period. So he traveled 50 miles, and he's on his way back home, it looks like. So 50 miles, And our hours here, 5.5 to 8, is going to give us 2.5 hours. So 50 miles, so a rate of 50 miles in 2.5 hours is going to give us 20 miles per hour. We divide that. Okay, next time period, we got two more from 8 to 9.5 hours. Again, going back to the graph, changing colors again from 8 to 9.5. Looks like he took another break. So we'll go in and fill that one in. So 0 miles again in 1.5 hours, that was. And then last, 9.5 to 10. Again, going back to our graph. Change colors one more time. So from 9.5 to 10, he went from 130 miles down to 100. So he went 30 miles. And traveled a half an hour, so a rate of 30 miles divided by 0.5 hours, and we're going to get that he was going 60 miles per hour. So 30 miles in a half hour, 60 miles he would have been going in 1 hour. All right, next one. Same idea, new situation. So the community swimming pool prepared the pool for opening day. The pool graph shows the depth of the water of the swimming pool after X hours. So why do you think the pool was emptied and refilled? Variety of reasons. You could fill in your thoughts there. Could have been drained to be cleaned, some repairs to get done, anything that would make sense as to why you were draining a pool. Okay, so again, we're going to label our time periods and our rate of change. So the first time period looks like it goes from 0 to 2 hours if we look back at that graph. And the water level remained steady. So remained at 7 feet. So it was not drained at all. And then we go from 2 hours to 6 hours. So 2 hours, I'm going to change it to blue now. 2 hours to 6 hours. And it went from 7 to 5. So drained from 7 to 5 feet. So 2 feet, so a rate of 2 feet in 4 hours means it was drained at 0.5 feet per hour. Okay, then our next time period was from 6 to 8 hours. If we look back here, so 6 to 8, now it's completely drained. So it drained to 0. So drained to 0 feet, or you could say empty. So we went from 5 to 0 in 2 hours. So a rate of 5 feet in 2 hours comes out to be 2.5 feet per hour it drained. And then point D, from 8 to 14, it remains constant at 0. So I'm just going to put remains at 0. So a rate of 0 also. And then we are then filled back up. So from hours 14 to hours 20, if I find that point there, it was filled back up to 9 feet. And that rate, 9 feet divided by 6 hours, it was refilled at 1.5 feet per hour, we could say. So just that rate of change, rise over run. Okay, C says, was the pool being emptied at the same rate the entire time? No. If we just look at that graph, there's multiple rates of change. And D, why does it make sense for the graph of this situation to be continuous? Well, for any given moment in time, there is a water level to record, even if it's a partial feet, like 5.5 feet. The continuous graphs only make sense when parts of a whole aren't going to make sense to the situation. So we could say for any given time, there is a corresponding water level. All right, from there, this is a little bit of a challenge here. I think it'd be a good time to pause it and see what you can come up with as far as you're going to take these situations. It says students at East High School are designing ceramic drinking cups for their art project. The students chose a variety of shapes for their cups. So they gave us these 6 shapes, and then on the next page, it says to test the cups, hot water is poured in each at a constant rate. The graph shown represents the height of the liquid in each of the cups. So the height of the liquid is going to change based off the shape of those cups. So if we're going to match those to the cups, again, I encourage you to try to pause it, see if you can make that match, then unpause it to check your work. So going through these, hopefully you've done that now. Graph A is going to match to Ryan. If we go to Ryan's cup's got a hole in the bottom, so it's never going to fill. That's why there's no graph there. If we go to graph B, it's going to match up most with Jacqueline. If we go to Jacqueline's graph, we can see that at the beginning, it's going to be filling. The height is going to go up quick, so we can see that rate's going up. And then the wider it gets, the height is going to slow down because the width of that is getting bigger and bigger. So the height that it's increasing is going to slow. So you see that curve and it's slowing. Graph C is going to match mostly to Blake. If we go to Blake's, his is going to fill up height-wise very quickly in the beginning. That's what that graph's showing. And then as it gets wider, it's going to slow down, just like that graph is showing. Graph D is going to correspond most to Timothy. And if we go to Timothy's, we can see it's going to, looks like it's going to start to fill a little quickly, and then it's going to slow and become pretty constant as far as that height going up. That's why it flattens out. And then at the top, it narrows again, so that increase is going to go up drastically like that's showing there on graph D. Graph E corresponds to Nico. So Nico, if we go to his, in the beginning, it's going to be very slow for the height to increase, but as it fills, the rate at which it gets taller is going to increase because that space is getting narrower and narrower. So that's why that curve, the increasing rate going up. And then F corresponds to Monica mostly. If we go take a look at Monica's, in the beginning, slowly, and it's going to increase, so that rate's going to go up. And then again, once it reaches that point, as it widens back out, it's going to start to flatten again as a graph, and that rate is going to slow down. So there's how we can match up the graphs to each one of those situations.